Curved mirrors. Flat mirrors create virtual images, while curved mirrors create real images. One basic type of curved mirror is the spherical mirror. A spherical mirror, as its name implies, has the shape of part of a sphere surface. A spherical mirror with light reflecting from its silvered concave surface is called a concave spherical mirror. Concave mirrors are used whenever a magnified image of an object is needed, as in the case of dressing table mirrors. Concave mirrors can produce both real and virtual images. Objects at a distance smaller than the radius of curvature form virtual images, while objects at a greater distance than such radius form real ones. One factor that determines where the image will appear in a concave spherical mirror and how large the image will be is the radius of curvature, r, of the mirror. The radius of curvature is the same as the radius of the spherical shell of which the mirror is a small part. R is therefore the distance from the mirror surface to the center of curvature, Z. To clarify, a real image is an image formed when rays of light actually pass through a point of the image. Spherical mirrors also cause a spherical aberration, a phenomenon in which rays do not exactly intersect at the image point, therefore making the image look different. The mirror equation. In order to find the distance between the object and a reflection, an equation is needed. This formula is called the mirror equation. It is defined as follows: 1 divided by object distance plus 1 divided by image distance is equal to 1 divided by focal length. This can help us find measurements in reflections and draw proper diagrams. Magnification. The formula for finding magnification is as follows: h prime, or image height, divided by h, or object height, is equals to minus q, image distance, or image distance, divided by p, which is object distance. For an image in front of the mirror, m is negative and the image is upside down, or inverted, with respect to the object. When the image is behind the mirror, m is positive and the image is upright with respect to the object. Ray diagrams. Ray diagrams are useful for checking values calculated from the mirror and magnification equations. The techniques for ray diagrams that were used to locate the image for an object in front of a flat mirror can also be used for concave spherical mirrors. When drawing the ray diagrams for concave mirrors, follow the basic procedure for a flat mirror, but also measure all distances along the principal axis and mark the center of curvature, C, and the focal point, F. As with a flat mirror, draw the diagram to scale. For instance, if the object distance is 50 centimeters, you can draw the object distance as 5 centimeters. For spherical mirrors, there 3 reference rays are used to find the image point. The intersection of any 2 rays locates the image. The third ray should intersect at the same point and can be used to check the diagram. Convex mirrors. Convex spherical mirrors take the objects in a large field of view and produce a small image, so they are well suited for providing a fixed observer with a complete view of a large area. Convex mirrors are often placed in stores to help employees monitor customers and at the intersection of busy hallways, so that people in both hallways can tell when the others are approaching. Parabolic mirrors. Parabolic mirrors are concave mirrors designed to eliminate spherical aberration. Parabolic mirrors are segments of a paraboloid, whose inner surface is reflecting. All rays parallel to the principal axis converge at the focal point regardless of where on the mirror surface the rays reflect. Thus, a real image forms without spherical aberration.